Bar, I have. It's a great pleasure to welcome you again to give one of your seminal lectures here.
Thanks. I start my talk here. I have been very concerned that when I give these talks, in course of time I have become very conscious that the people doing this general area seem to be divided in two camps. Okay? And the interface between the two camps seems to be very minor. Okay? I mean, one camp who do people like string theory and matrix models, and they all end up by doing different functional integrals of various kinds. Okay? And the interface which go into quantum field theory, for example, algebraic quantum field theory, where also certain developments are taking place, seem to be disjoint almost from the other camp. There are some people who are not ideologically pure, and they go back and forth, but there are very few of them. Okay? The result has been that whenever I give this talk, depending on the audience, they will follow me. Okay? So I am concerned about this issue because I will be talking about basic quantum field theory, but I have to assume that people here are familiar with, for example, constraint theory or gauge theories or a BRST model, how to quantize quantum field theory using BRST, what is the function of Gauss law, or developments which have taken place for a very long time, starting with, I think, already from Tom Kibble, that quantum field theory is infrared QED.
I can see you. Okay, thanks.
Yeah. It has been known already from papers which are quite old, from Tom Kibble, going down to Froelich, Mortio Strachey, and now coming down to people doing algebraic quantum field theory, that because of infrared effects, very dramatic things happen in QED and QCD, involving breakdown of Lorentz invariance, involving breakdown of Lorentz invariance and perhaps also of CPT theorem. So these are developments which are quite old, but nevertheless they seem not to be diffused in the audience which are in the other camp. It looks like two ideologically disjoint camps. And let me confess that I belong to the algebraic quantum field theory and standard quantum field theory camp. I prefer that. I find it more coherent, so I'll stick to that. So if there are questions, I don't want to exceed 1 hour. If questions arise, I will answer. I doubt very much that I'll be able to say the kind of things I want to tell you, but I think that something new has been happening due to recent developments which come from discussions of superselection sectors in quantum field theory. By the way, this has direct implication for example, work in quantum manifolds with boundaries, where you have boundary effects, you have surface excitations. They seem to be corollaries of the kind of things I will be talking about in terms of superselection sectors. So all those things can be covered by an overreaching set of ideas coming from gauge theories, and I will discuss some aspects of this situation to you now. Okay? So to go forward, so there are questions I will stop, but go no. It's not changing.
I'm not sure
what's this?
I'm not sure whether people online can see the
but it's not changing the page. You have to come here and help me because okay. So what I want to do now is to discuss for you a new I think it is a new mechanism for confinement and deconfinement transitions in QCD and QED. In the context of QCD, okay, in the earlier work we have done, I have given the reference here, mentions some of these aspects. In the case of QED, I did some work several years ago with Sachin Vaidya at in CHEP in IISc, where we had talked about sky group, and the history of that thing is that much before that, Abhay Ashtekar and I think Abhay Ashtekar and a colleague of his had discussed what they call the sky group, okay? And somehow our ideas are emerging or coming from that tradition, okay, which is going back to the work of Abhay, Hanmani Ashtekar, and this other colleague of Abhay, whom I don't remember. So that is the history of this thing, and I try to briefly tell you what these things are. There's something strange. It's not changing.
It's not set, but I don't know what's going on.
Again, it is stuck.
I don't think the participants can see the screen now.
What do you do?
It
If this works, you
can
This works.
Yeah.
Something went on. How do I do it?
This is this is forward. This is
And if you point towards that, no?
Can you tell if they can see the screen, this slide, or something like that?
Send a message to the audience to ask if they can see the slides.
Something.
Screen has disappeared. How can it be?
I don't know.
This should come on.
It may have to do with the switch you made.
It's hiding over there on the left.
Let's see if I can find Jeff again. Just
It is very strange. It's connected.
It is connected, but there is nothing there. It should be there. It is on.
I don't know what's happening. So maybe we should reschedule the seminar for a later date.
Yeah, probably when the IT stuff is available.
I think we need IT staff here for this seminar.
This screen is shared, but there is nothing there in the projector.
No, but where is the screen shared?
There is a share screen, no? There is a share screen option. Is he coming?
Then
no, apparently he has to listen to something online, which and he's not willing to help. It's as simple as that.
He came back.
Somebody must have pressed that by accident or something. I don't know whether it's visible online or not. Sorry.
So, okay, I hope that the people on the line, offline, online, can hear me. Okay.
They can hear you, but I don't think they can see you.
Now they should be able to see me, right? Am I right?
I don't think they can see it, but let me try it. Let me stop sharing it and try sharing again. See if we can, because I can't see it from the. Let me see if I can find your talk over there and start this bit. This is. Okay. Now, let me try sharing one more time and see if I can pick this up. Share. Share that one.
Yeah, it's coming to your.
Okay, then that's better.
But
Sorry?
yeah, it's,
It was sharing them, so I don't know what it was doing.
Yeah, your screen is there, okay.
yeah, his screen is in your laptop, so.
And your screen is working down there.
Okay, then they probably can't
All
see
right,
it
otherwise
this
it's
time.
They can see it, you mean?
I think they can see it now. So,
Now
with this
it's a
history.
bit too large.
Let's try it a little.
Okay.
I don't know what's.
Yeah.
Yeah, let's
It's
try
not
that.
changing. So press it doesn't change.
I don't. If you can try moving it that way, it probably will work.
So how do I go back?
Space bar is forward and
Go back.
delete is reverse. Delete. This one.
Okay.
This is back.
That's
forward.
back.
This is back. Back.
Okay, I got it. No, I can use this. Okay. Okay.
Sorry.
So let me, and they want to see me, where should I stand here? Can you see me?
They can probably see you in the middle, somewhere in the middle, if you stand right near the lectern.
Okay. So this is by way of introduction. So I have given the reference for our review, which I wrote with Andres Reyes-Lega some time ago, which sort of summarizes a work just been going on for a long time, especially starting from Chern-Simons, our analysis of Chern-Simons models, and before that, as I told you, the work of people like Abhay. So, what I want to emphasize that when we talk about gauge group, the gauge group is not the compact Lie group which you are dealing with, like SU3. That is not the gauge group. The gauge group is the group of maps from your space-time which you are integrated, looking at, which I denote here by script G. And what you are involved in is the group of maps from space-time to a compact Lie group G. Okay? Or if you are dealing with, say, quantum gravity and you are dealing with Balachandran action, for example, it will involve group of maps from script G to, in that case, SO31 or SL2C, PSL2C. Okay? So the tangent space group, which is PSL2C for the Balachandran action. Okay? So that's quite a different beast that we are dealing with. And the situation I am going to deal with corresponds to the. So if you give me an element of the script G, this is a gauge transformation. G at each point of space-time gives you an element of the group capital G, and as x goes to infinity, I will assume that it approaches some element h of x hat of the compact Lie group you are dealing with when x hat, when this coordinate x goes to infinity. Okay? It could happen that it has no limit. Okay? I have not investigated that case, and it will have some new consequences which I will not deal with. Okay? I have not studied it, so I don't want to see it. But I do want to consider the case where G approaches some element H, which can depend on the limiting point you are reaching at infinity, and that will play an important role in the analysis. So, then the standard case where you deal with things like SU3 or U1 of electromagnetism corresponds to only to the case where G approaches a fixed element H of infinity, some fixed element of the group U1 or the group you are dealing with. But we want to consider the case where that is not the case. Okay? So it actually depends upon the limiting point, and we can look at the topology of the limiting points that if there is time, I'll talk about it. Okay. So that is by way of introduction. Set up. Okay. So this is giving you the notation. Okay. So I will deal mostly for convenience. For example, with this union, which is a non-abelian group, and the connection form that I will write is A mu, which is a Lie algebra valued connection, which in some basis lambda alpha, for example, the Kelman basis, with a canonical normalization, that trace of lambda alpha lambda beta is twice delta alpha beta in, say, the defining representation is what I will use. The normalization will not play any role, so I'll just put it there. And the field that is conjugate to A, I denote as E, and that is also Lie algebra valued form, one form, and usually it is interpreted in electrodynamics as the electric field. Okay? So if you are dealing with U1 QED, what happens is that we can U1 case, you don't have any lambda alpha, it's a fixed number which you can take to be the charge you are dealing with, and we shall see that this leads directly to what is called the chemical potential in finite temperature field theory. Okay. The big player in this game is the Gauss law. Okay. Now I have to spend some time on the Gauss law because the distributional character of the Gauss law will play a role here. Okay. So the infinitesimal transformation for the Gauss law this can be written as Q of cascade, where cascade is a Lie algebra value test function with which I smear the standard Gauss law, which is the covariant divergence of the electric field plus the J0. J0 times, I have missed here, yeah, this is correct. The covariant divergence of EAR plus J0, but I want to smear it with a test function cascade. Okay? So I have put a test function, and it is Lie algebra valued. So the brackets and the two ends indicate that I am also taking a trace over the Lie algebra, which you have chosen at the very beginning. Any convenient trace is fine. These are finite dimensional compact Lie algebras, so they allow a trace function. So you use that trace.
Why is it integrated only from 0 to infinity and not minus infinity to infinity?
Sorry, I can't hear you very well.
Why is it integration from 0 to infinity and not from minus infinity to infinity?
That's a mistake. Oh, thank you. That's a typo. I didn't notice it at all. Okay? Then just include this spatial slice. Okay? I can generalize it to space-time regions. Let me avoid that as an extra complication. Okay? That is simply an error. So okay. So when you apply the Gauss Q cascade, we are assuming that all such cascade, all such test functions are allowed. Okay, so this is not one constant operator, but a family of constant operators depending on the test function. Now I don't want to write like this. I don't want to write the Gauss law like this, but I want to write it in a slightly different way. By partial, if you like, partial integration. But so instead of writing the covariant derivative on the electric field as I did in the previous equation, I want to write the covariant derivative on the test function and write it in this form. Okay. The reason for this test form, writing like this, is because this electric fields are distributions. Okay. So distributional derivatives are normally interpreted as derivatives of test functions, so I prefer to write it like this. Okay? And there are definite advantages in doing this. Some of you who have studied a little bit of, say, the Laplace operator on a manifold with boundary, you may know the weak solutions of the Laplace, operator to given boundary conditions, Sobolev spaces and so on. There also the same thing is done. And so I am, if you like, taking ideas which are already known in some branches of mathematics, in the treatment of PDEs, the partial differential equations in mathematics. So I write like this, and the idea is that at least classically we would like this Q cascade to coincide with the standard Gauss law and hence vanish on the space. So whenever this test function vanishes sufficiently fast at infinity, I will assume that this Q cascade goes to 0 on the allowed quantum states. Okay. So this is an operator. Okay. This is an operator which is given on the full Hilbert space. Okay, for sure. Okay. Now, what we want to do is to take a state on which this Q cascade vanishes. Okay. When cascade goes to 0 at infinity. Okay. So pick one, that's what we normally do. Then if you want, you can, for such cascade vanishing at infinity, you can take any quantum state and do a GNS construction. That is, there's a canonical construction that if you give me a state on an algebra, I can find the Hilbert space on which this algebra operates by a well-defined procedure which is of vast generality. So you can find the entire state. Okay? So that takes care of gauge fixing. I don't fix gauges. Simply do a GNS construction, you will get the answer. But I don't want the details of that here. But if the importance of this Q cascade, which is very important for me, is that this operator now can be extended to a larger set where these cascades do not vanish. They are Lie algebra valued functions at infinity and they don't vanish identically. Okay? So if the Q cascade does not vanish at infinity, this is no longer a constraint on the quantum states. For example, if I am doing QED and I take cascade to be a constant function, so it doesn't vanish at infinity in QED, then you see immediately that what I have written as Q cascade is just the chemical potential.
Just on the point of helping the younger people, the word cascade is being applied to this Greek symbol, which is not normally called that. That's it.
So,
the younger people might not know what you mean by the word cascade.
cascade is this thing.
There's a capital X here.
This one.
Capital Psi.
This is cascade, no?
It's called cascade.
It's in practical physics called the
Is
cascade.
it not called cascade?
That symbol is used.
Yes, but Charles's point is that the younger people would know that.
Yeah, but they're not super.
What do you want me to call it? I'll call it.
You can call it cascade and just emphasize what it is.
This is what I call cascade. Sky is something else, like this.
Psi.
Sky is, you want me to call this as sky?
No, call it cascade. Just
You call it Okay.
I was wondering.
Okay.
Whatever.
So let me come back to this. So I want to see, you can see that this is a gauge transform. Suppose I am doing QED, okay, and I particularly choose a test function where these functions cascade are constant all over space. Then you see that the first term becomes 0 because the covariant derivative is just a constant function. So you get for quantum states where the electric field vanishes at infinity. So let me say, I will not use classical language. I will consciously try to avoid classical language because I think there is only one theory and there is quantum. Okay? The fact our criticism of seeing classical is coming from some theory of observations which we have still not properly understood. Okay? There is no collapse of the packet or anything like that, in my opinion. So, with that in mind, I will say that electric field vanishing at infinity means that there are quantum states where the expectation value of the electric field goes to 0 at infinity. In that case, you can do a partial integration. Cascade is a constant, or in fact in QED, the cascade is a constant. Di of the constant is 0 anyway, so I don't have to bother about it. And I am left with this term, and that is what we call the standard chemical potential in finite temperature field theory. But this term is already existing in ordinary QED as a generator of U1 gas transformation, global U1 gas transformations. Okay? And what we call sky group with Sachin some time ago was the case where these cascades that I am writing in QCD goes to some functions at infinity. So you get, or even in QED, they go to some functions at infinity. So it is not merely testing the overall flux in appropriate quantum state, the overall flux of the electric field. It also is measuring the moments of the electric field at infinity. So will they be 0 or not? That depends on the quantum state you choose. Okay? It's not up to you there are point of states where it vanishes, and there are point of states where it does not vanish. So all these are covered by the statement that we get this Q generates in QED or QCD a group. This is a Lie algebra value. It is a generator of a group where this cascade may not vanish. It gives you non-trivial functions at infinity. And later, I don't think there will be time, but there is some development which comes actually from the work of Georgi Mitzi. I wish he could hear me, and also by people like Weidman, Klaus Kemp, and so forth, where this test functions I am getting in infinity generate an appropriate abelian algebra on which an observation can be placed. In fact, also by Sergei Dobricker, I should say, where observations in quantum theory may be formulated in terms of these functions. But I will not go into that today.
Where is the surface term when you do the integration?
Surface terms. I don't know anything about surface terms. I don't do partial integrations, period.
I thought you had partial integration.
No, I interpreted the original Gauss law like this. I think this is the correct way to write Gauss law. I wrote the first equation to indicate to you where this comes from. I will show you that this equation is what you get from Lagrangian. If you do Lagrange transformations, this is what you get.
So if you integrate by parts on this, you do not get the original Gauss law.
If I do partial integration, imagine everything is classical, yes. But these are quantum operators, distribution valued quantum operators, and I don't know anything about partial integration.
The surface term.
I don't know anything about surface. Quantum fields cannot be pushed to surfaces. Yes, they are distributions.
Classically, there's a surface term.
Classically, it is a surface term.
And that plays no role here.
I said again, I don't want to talk about classical physics because I think it is very ill-formed.
There could be physics on the surface.
That will come out of this. It is like legging. Take all functions on the two sphere, smooth functions on the two sphere. It is an algebra, C-star algebra. You can make it into a C-star algebra. Or smooth functions, bounded norm, and so on. Pointwise multiplication. You ask, is there a subalgebra of functions living purely on the equator? Or that algebra? The answer is no. Because that subalgebra will consist of delta functions. That is not part of your original algebra. So how do I describe things on the boundary? You can't do the restriction of the original algebra to the surface. It doesn't exist.
There's no boundary in that discussion.
What?
There's no boundary in that discussion. An example.
Use this.
I will not. My hearing is not so good. But so
You took an example of the surface of the sphere and the equator. Right? Surface of the sphere has no boundary.
I am only working on two sphere. This example was on the two sphere and its equator. The two sphere allows smooth functions in the two sphere.
Yeah, I understood what you said about that, but I don't see how it's relevant to what Brian asked.
Here the corresponding thing is, what will happen is that the algebra I get living at surface at the infinity is a quotient algebra of the once the algebra where cascades vanish at infinity. Okay, it happens to be a subalgebra. Okay, that's a smooth, and they vanish in the quantum states. So the effective states, operators, effective Qs which act there are equivalent classes of Qs, modeled by test functions which vanish at infinity. Likewise, on the two sphere, to get any representation of the algebra on the equator, you take all functions on the two sphere and those which vanish on the equator and take the quotient algebra. The quotient algebra is equivalent class that is well defined on the equator. But that is not the original algebra of delta functions on the equator. Likewise here also. So this is a matter of, for example, this is considerations of this kind is what leads to divergences when you apply Dirac's procedure of applying Gauss law on quantum states. And it is somehow avoided when you, by the time you end up with BRST and BV. Okay? They deal with equivalence classes. If you check, I think they are called Koszul equivalence classes, Koszul resolution of an algebra, if I remember correctly. So the conceptual framework is different. Okay? I don't do partial integrations with distributions, if possible. Sometimes you are helpless, then you do, but avoid it. If you want to pretend that we are doing quantum theory, we should do quantum theory. I think. Try it. Okay. So I tell you what we call the sky view. Okay. Now the main point is this you can check. Okay.
No, it's this one, this.
I want to go back.
This.
Yeah. You can easily check that this Q cascade generate gauge transformations on all local fields. The local fields, if you take for example electric field in a spatially localized region, not in local field, I mean take one of these operators, smear with test functions which are supported in a finite space-time region, and take the commutator with Q cascade, you'll find that it is generating gauge transformations. No more. Okay? Because it doesn't care what happens to the test function at infinity. It will simply change that, say, potential, the connection form by going into a cascade. That's it, okay, locally. So one consequence of this is that whatever be the asymptotic behavior of cascade at infinity, the equations of motion will commute with these operators. Okay? They won't change. So if an equation of motion is, say, d mu of mu nu equal to 0, you're right, then see what happens to it if I apply Q cascade on it, say exponential of the Q cascade on it, conjugated, you see that the whole thing changes by homogeneously with a gauge transformation, which cancels out because one side is 0. Okay? So this operator and the group it generates will preserve all equations of motion, okay? All local equations of motion. It also preserves the standard quantum Hamiltonian of QCD. So that is not a problem. Yeah, so here's what I'm saying. This point has been argued by us, not only by, I should again say that this kind of thing has a history which goes into more formal minded people like Abhay. Okay? And I suppose it also goes even, certainly it goes back to the papers of Froelich and Co. and also papers of Buchholz, okay? And Freidenhagen. There are so many people and they are quite well aware of this fact. And actually there is a very nice paper by Buchholz which treats this Gauss law in a very rigorous context. Okay? So the important consequence I want to emphasize is that whatever I do with Q cascade, even if test functions don't vanish at infinity, they will preserve equations of motion. They are in the commutant of the equations of motion that you are dealing with, always. So this is because of the locality of the quantum theory. Gone.
Sorry, what are you trying to do? Go back. Sorry.
What do you do?
You tell me where you want to be.
Okay. Go further.
Go back further.
No. Start with the novel chemical positions.
Yes.
This one, no.
Next. No, don't.
Okay.
That is. It's these two.
Next. Before that. Yeah. Before. There was a big title, chemical. Here it is. Okay. So now I have told already that the Q cascade I am writing, in case cascade is a constant in QED, is in fact the standard chemical potential that people use. Okay? In QED, in QCD, that is no longer the case. Okay? Because cascade now is a Lie algebra value function, and this Q cascade will generate the SUN group, and it also will generate this maps at infinity to SUN groups, as you shall see in a minute. Okay? But they will not affect the equations of motion. Okay? So what I want, maybe the language is misleading. I will call Q cascade as the non-abelian chemical potential. So this may be misleading, but I am willing to change the name. This appears to be the most appropriate phrase I can use. So let me take with H0. I don't care about H0. I will not touch it. H0 is the standard QCD Hamiltonian. This is the Hamiltonian which is asymptotically free, and if you apply Hamilton's equations, you will get equations of motion of QCD. Okay? I don't want to touch it. It will have all the problems of renormalization and so forth. I don't want to touch it. Okay? So that is my H0. If you want to do finite temperature field theory, it is H0 that is used normally. Maybe with a normally you put in extra terms corresponding to the number operator, but now I say that is not enough, because you can add any Q cascade to it, which generates these gauge transformations with a scale because H0 has energy scale. There is a scale mu which has to be put in front of Q cascade and put in some energy scale and put it in H. Where does this energy scale come? I'll come back if there is time to interpret this term, where it comes from. We will try to give a physical interpretation of where it originates. So the main point I want to say is that the new term I am writing will not change equations of motion, because as I told you, this Q cascade doesn't change equations of motion. It will also commute to the zero. The two terms I am writing in H are mutually commuting. Okay? Nevertheless, they will influence dynamics in the colored sectors, which I will show you how. Okay? So this is the H I want to consider, and I will claim that this is, if correct, there are some many consequences. Okay. I should say that before us, which is after I gave some seminars, it was pointed out to me by Parthasarathi that this they have considered chemical potentials of this kind before, okay? But in the context of QCD, non-abelian theory, in the context of what people call as the sub-T vacuum. So they were doing finite temperature field theory and seeing what will happen if you put such terms. So there is a literature on this. I give it a reference, but the literature is extremely limited. So here I have briefly hinted what this extra term, where this extra term is coming. The origin is very much same as how the standard chemical potential comes in QED. Okay? Who makes it? Where does it come from? So the interpretation that is emerging from us, at least, is that it comes from an experimental setup which is trying to see the system. Okay? So it is describing an experimental setup which is living. Notice that Q cascade effectively lives only at infinity, because all the cascade which vanishes in the bounded region vanishes on the quantum states. So it is telling how the experimental setup sitting outside the interaction region is looking at the system, how it is coupling. So by reading it, we should be able to get data on how the system evolves. Have we solved the problem? No. But that is a model which has been emerging from various papers, including I think basic papers are here. Giorgio, she's there. Then Giorgio wrote about phase transitions, which I will talk here.
Yes, ciao.
He's listening.
See, there, no? Giorgio.
Yes, of course I'm listening. What do you think?
Okay, so these ideas come from Giorgio, and I can adapt this kind of thing to the kind of Giorgio's work, for example, for ferromagnetics. He was talking about second order phase, first order phase transitions. We will see that these superselection sectors automatically create these phase transitions. So things like phase transitions in this language or spontaneous symmetry breakdown anomalies that she talked about they have an overreaching theory that any operator which changes the superselection sector, which will come to now, is an anomalous. That's it. There are infinite number of anomalies in these models. and I'll show it to you what they are as we go along. Okay.
I'll do it.
Okay. Now, if the non-abelian target group G, let's such as SU3, is of greatest interest, it turns out that the commutator Q with two test functions cascade 1 and cascade 2 don't commute because they are multiplied by these Lie algebra elements. So you find this equation that Q of cascade 1, Q of cascade 2 commutator is I times Q of cascade 1 and 2. Okay? So this is a non-commutative algebra in the non-abelian case. But they commute with all observables. They commute with equations of motion, all local observables, they commute with the x0 Hamiltonian. So in a superselection sector where we are observing only local algebras, we should diagonalize these operators, but we cannot diagonalize all of them because they are not commutative. So Dirac has taught us that what we should do is to diagonalize a complete commuting set. Let me do that. I will show you the choice of Q cascade. For example, you can take Q cascade for SU3. You can choose the test function cascade to be a linear combination of, if you know the language, the two commuting operators of SU3, which is normally called as lambda 3 and lambda 8. Okay? Multiply by smooth test functions at infinity. So, and assume that the cascade you are putting in the Q cascade have boundary values which are linear combinations of lambda 3 and lambda 8 with test functions which have certain values at infinity. I don't care what happens in the bulk. And they will commute after taking care of the fact that the Gauss law is fulfilled by your quantum states, they will commute. You can diagonalize the following Dirac. That's an example. In general, these are infinite dimensional Lie algebras at infinity. So we have to check what is the center of this algebra. It can be quite large. But there is one point. I have added this new cascade to the Hamiltonian. There is no restriction on what I add to mu cascade. What I diagonalize and what I put in the Hamiltonian are two different things. So when I put this term in the Hamiltonian, Q cascade, and I look at time evolution, you can change the diagonalized operators defining the quantum state, which I will write down in a minute. So what is the meaning? You are changing the complete commuting set you are diagonalized, but if you change it, each complete commuting set diagonalized defines a particular superselection sector because no observable can change it. Nevertheless, this chemical potential will change it. So these chemical potentials are evolving the superselection sectors. This is this evolving the superselection sector is exactly what is called in another language as phase transitions. So you have a continuous choice of phases here because this is a continuous group, so it will go on changing it. So this Q cascade are creating continuous phase transitions as time is evolving, and because I am changing the phases, there will be consequences for the expectation values of observables. So this is somehow modeling what Giorgio was talking about in his old papers. Okay? Giorgio and Fiorini were talking about in their old papers, and also what I think Whiteman was talking about, and somehow Sergio Doppler's paper also seems to be bearing on this. Okay? So I will give you how it happens. So I will show you that the generic choice of mu cascade will create an orbit in the diagonal states. These are all, at least in simple models, generate an orbit which is ergodic. It never comes back to the original situation. And some discussion I had a couple of days ago with Denjo and Brian, it seems that I can model it. Certainly I can model it with the orbit of R real line on a two torus. You may know this winding torus, okay, winding things. which is dense on the torus, we can actually model what is happening here along those lines and explicitly compute what is happening. So, in certain cases, in general case, I don't know the answer, okay? But it will evolve, and it seems that in the model that came in this discussion, we can even find a fixed point or this ergodic orbit. A fixed point means it will come very, very near to some fixed point. So, I will show you how this happens. But what is most interesting is that there are also other choices of this chemical potential where nothing moves. For example, I can diagonalize some operators of two cascade to give the superselection sector and put the same operator in the Hamiltonian. Then it should not change at all. In that case, the superselection sector does not change at all. Okay? So what I will argue is that in the former case, the average value of color observables are all 0. Where the orbit is ergodic, the expectation value of color observables are exactly 0. Whereas if you are in the second case, it is not 0, you can see everything. So I want to call the first situation as a color confined phase and the second one as a color deconfined phase. Yes.
Now, can you, because I didn't really understand, repeat the average being 0 for certain state? Can you repeat that argument again? Can you repeat the argument you gave for the average of the expectations being 0 in case 4?
I will do it now.
Okay.
I will give you why the expectation values go to 0. I will show it to you. Okay. We can actually calculate in cases. It's Poincare theorem. Poincare, yeah? Before I go on, I want to tell you that this term is already there when you do Legendre transformation from the Lagrangian. Okay. If you do the Lagrangian Legendre transformation, there is a term in the Lagrangian which is f mu nu f mu nu, trace of f mu nu f mu nu, and that is a term let's say fi0 fi0. Okay. So when you do the Legendre transformation, fi0 is covariant derivative of a0 plus some other term, I don't care about that, multiplied by fi0, which is the electric field. Okay. So that is this term, the first term. And a0 j0 term is already in the Lagrangian, in the interaction mu jb. It's already there. Normally what we do, if you do Dirac's constraint analysis, is to say that if they recklessly we do partial derivations, put a0 in front and say the canonical momentum of a0, pi0 is weakly 0, take the commutator and say that this term goes away. So we have recklessly done partial derivations without telling why this a0 should go to 0. a0 is effectively a classical function because it has no canonical momentum in the Lagrangian. But who told you that it goes to 0 at infinity? We just do it. Okay? We just ignore the fact that maybe there are test functions which do not vanish at infinity, and that is the case we are considering here. This a0 is what happens to become cascade in my calculations. Okay? Cascade or psi or whatever it is in my calculations. Okay? So this term is already there, okay? And we had noted this fact in the original paper. And I just want to remark that there is no reason to be surprised because it is there. Okay. But you can be convinced, you can be concerned that I am adding to x0 this extra term. Okay. This term is what I am reading to x0. Okay. So if I write it as a 4 momentum p mu, the standard p mu coming from energy moment tensor, I am adding this term. Okay. But this term involves first a test function cascade is a function, and secondly it is added only to p0. I am not adding it to the momentum. Momenta are not changed. If you change momenta, spatial momentum conservation will be also in trouble. But if I add like this, the p mu, you can see the extra term, this does not transform like a 4 vector under Lorentz transformations. So what is the consequence? Lorentz invariance is broken. How much is it broken depends upon the magnitude of mu. So it is, if you like, the effect of the fact that I have an experimental setup which chooses the frame, could be like that. But should we be disturbed? But we know, as I told before, the Lorentz symmetry is broken by very independent considerations by algebraic quantum field theory people. It has been known for a long time, and they prove that what Lorentz transformations does is to change the superselection sector of QED. Their main proofs are in QED, and Lorentz transformations change the superselection sector. The effect in their calculations is coming from the fact that the infrared cloud, which goes all the way, so infrared cloud that is going to infinity, if you make a Lorentz transformation, they change. The change of the infrared cloud at infinity cannot be accommodated by any local operator. So that is their formulation of the problem interpreted in our language. But this similar thing is happening here. Because these are all infrared effects coming from things happening at infinity. So these are coherent, and I think that there is no reason to be overly concerned that Lorentz invariance is gone. I think Lorentz invariance is gone from infrared effects, but will I see it in local experiments? I don't. There are certain things where you can see, but you cannot see really only do local experiments. These are infrared effects, so one has to have access to what is happening very far away. And are there physical effects of that kind? I think there are, but we will discuss it later. Okay. So I given the reference to the original papers. The classic, very classic long paper is definitely due to Luke, Froehlich, Mortius-Stroke. Before that, I think Tom Kibble's papers are very powerful papers in discussing issues or domain problems of quantum fields in a very careful way. And recent papers by Mundred and Schroer also discuss it in a careful way. Okay. So I want to discuss this dynamics. So I will just do that, and I will not proceed further because there will be no time. Okay? So what about dynamics? How does in quantum field theory there are always two aspects. One is the quantum state. It tells you the objective situation of what you're looking, what is coming out of your say LHC, the story, the ring at CERN. Okay, what is coming out? Okay, and what the experiment measures are the observables the experiment measures. The number is a coupling of the state to the observable that gives you a number, which is apparently what is registered by your detector. Okay, so I have to give you the state, and the observables are given to you from a priori. They are the local observables or the algebra of the system you are looking at. That is what you are looking at. That is the assumption. And the question is, what is the state with which I am going to? How is the state going to evolve under the Hamiltonian? Okay? The Hamiltonian is a time translation operator that comes from the fact that your translation invariance you have the P mu operator in the theory. Even if the Lorentz invariance is not there, P mu is assumed to exist. At least P0 is assumed to exist for time translation. Okay. So here I was therefore telling that if I want to go away from and also diagonalize things like color, okay, I have to diagonalize a complete commuting set from the sky blue, which is coming from the large, what we call large gauge transformations. So what are people call large gauge transformations are exactly those where these test functions don't vanish at infinity, and I have to diagonalize a complete commuting set from this large gauge transformations which form an abelian algebra. Okay? So I am repeating the statement here. This is what we do, for example, in QED. The conventional choice of Q cascade is a multiple of the electric charge operator, which is a part of this situation here. So the two things are coherent. So in QCD, what are the superselection operators? The situation in QCD is much richer. I don't have a full control. It is an infinite dimensional non-commutative algebra of Q cascades. Infinite dimensional because you have all these x's functional dependence available on the sphere at infinity. It is non-commutative because each function you are getting is Lie algebra value. They don't commute. So it is infinite dimensional algebra. And if you ask me what is a complete commutative set, I have to have knowledge of the center of this algebra. Do I have a full complete control of the center of this algebra? No, I don't have it. But I know examples. I can classify some of them. So the first thing you realize is there are complete commuting operators in the center which come from the quadratic and cubic Cartesian invariants of SU3. They certainly commuted everything. So I am ignoring the fact that the function dependence on x is also can also enter. I don't know how to control. It is that by itself is an infinite dimensional C-star algebra, and I don't have a good control on the C-star algebra business. David, if he had been here, would have known better. But I don't have it here. I don't know so much about this representation theory of C-star algebras. A non-commutative C-star algebra, I don't know. So the quadratic cubic Casimir invariants are certainly commuted everything. All these operators. Then normally for SU3, I can choose, as you know, I can diagonalize. You can pick a particular Cartan subalgebra. There are infinity of many Cartan subalgebras in SU3 Lie algebra. Pick one. It is a rank 2, so lambda 3 and lambda 8. So to pick lambda 8, you have to also pick out a preferred SU2 subgroup. So lambda 3 is the third component of isospin of the preferred SU2 subgroup, and you have to pick a lambda 8. And I can choose for cascade the test function linear combinations of lambda 3 and lambda 8. And let me consider a case where I take constant functions, smearing them out, because I can handle them like I do SU3. So I am going to consider the case. So I can also put any arbitrary functions there. And if I choose that, I can choose for the sky operators, which will diagonalize the particular superselection sectors by a cascade tilde. So Q cascade tilde is a linear combination of I3 and Y with coefficients becoming functions of some unit vector in infinity. So I want to see what is the consequence of this situation. So I am going to consider the case where lambda 3. So the superselection sector I am going to consider as an example of what people like Giorgio considered is labeled by diagonalizing the third component of isospin and hypercharge. And in a particular irreducible representation of SU3. It could be 3 star, whatever it is. Now, a generic Q cascade in the Hamiltonian will not commute with these operators. It can be any combination of these generators. And I want to see what will happen, how these things evolve in time. Local observables. By the way, local observables are not touched by this because they are controlled by H0. These things commute with H0. Don't touch it. It will only change they won't change equations of motion. They will change the superselection sector or the QCD generators you have diagonalized. And in fact, for a long time ago, in fact, I gave a seminar here that QCD is spontaneously broken because of this fact. Here, I think. And later, with Parameshwar and Sachin and so forth, we wrote a paper where we discussed this in some detail. So, notice again, I want to now go why there is a color confinement that is emerging from here. So, the generic non-Hamiltonian chemical potential will not preserve the superselection sector. So, generic non-Hamiltonian chemical potential will change the superselection sector. You can call it anomalous. So what we call anomalous these days is any operator which changes the superselection sector. We may say it is coming from some F with F dual or whatever it is. Its simple meaning is it changes the superselection sector. How many operators are there which are anomalous? There are uncountably many such anomalous operators. Okay? You can write them down. Okay? How many phases are there in QCD? There are uncountably many phases of QCD. There are uncountably many phases of QED. Okay? Let me go back. In QED also, people plot temperature versus chemical potential. Okay? Where the chemical potential is the number operator. We are claiming that that is not enough. You can take any test function which goes to any function of x at the boundary, and you can start writing multi-dimensional plots of this kind. On one axis is temperature, on the other axis is number operator, and the other axis is some operator which corresponds to, roughly speaking, to measuring the moments of the electric field at infinity and so on. It's an infinite dimensional space. Okay? For example, you can choose a cascade which goes to some spherical harmonic at infinity in QED. That will give some moment of the electric field at infinity in the quantum state. So you can go on writing this axis. There are infinitely many of them, and I don't know what a plot will look like in that case. Okay? I have not seen any such plot in the literature. That's the point. So here, in the very simple case I am considering, you can certainly tell what is the color representation you have diagonalized. What is it?
Oh, sorry.
No, not fully.
Okay. What is the color representation you have diagonalized? You can tell. You can tell because the Casimir's are okay. They don't change by these things. You can tell whether it is 3 star, 8, whatever it is, you can tell. Because they are color singlet, nothing will happen. They won't be touched by this Q cascade, mu times Q cascade I put in the Hamiltonian. They won't change at all. But can you change now? Okay. So as I say, the second possibility is I can also choose a Q cascade in the say chemical potential which commutes with the diagonalized operators. Then nothing will change. Okay. So there are these two possibilities. The second possibility is what I will call color deconfined state. Nothing will happen to color. But the other one is not that is not the case, and I want to discuss that further. So if you can change it. And I do that and I then stop. Okay? People say the color is confined. And they do some Wilson loop and potentials. But I don't think that's not a quantum statement, that's some kind of classical statement. Okay? That is for me highly inadequate, and anyway, it only applies to heavy parts. What happens to gluons? Okay? I don't know any such criterion even there for gluons. I think what it should mean, I suppose, is that if you take the Hamiltonian of QCD, defined no matter what, there are no colored states in the domain of that Hamiltonian. Okay? That's a well-defined statement. Domains are not such esoteric objects, and if the colored states are simply not in the domain of that operator, it seems reasonable that color is confined. But I know no such proof. Okay? And I don't know whether people doing numerical work with Wilson lines accomplish anything like this. I don't know.
I think the statement is that there would be a mass gap. There's a mass gap.
Yes. Then I don't know what that means.
Why if you prove it, you get a million. You can get a million first.
I don't know what that means that you can't see color. Mass gap, I have no problem with mass gaps. Okay. That's a different statement. I have nothing to say about that. Okay. This is what I was also told when I talked to people in IASC who do numerical work. And I accept it, but I don't know what it means in the context of confinement. I do know, this is very strange.
It means that there are no states below the mass gap.
Above the mass gap, there may be colored states.
It's a separate story.
So, I do know people doing clock.
Sorry, can I ask one question? Okay, so if we go as far as your previous slide, and we take that statement about confinement, now I want to ask a question. Do you know what happens? Maybe you don't like Wilson loops, but do you know what happens to the Wilson loops? Do they obey an area law or a perimeter law?
I have no idea what they think, what they mean in quantum theory. Because they are not classical statements. I don't know how to interpret them. There may be. I mean, as I say, there are two camps, and never the twain shall meet. I don't know what that means in terms of operator theory.
I think they're quantum statements. I think they're quantum statements. I don't think they're classical.
You give me a quantum operator which gives that answer, I will be happy. I'll take it.
But you see, you should.
Quantum theory has only operated quantum operators, distribution value quantum operators, or maybe phenomenologists and quantum states on it. Show me what that means here.
No, I mean, you're doing work. I mean, you should sit down with a sheet of paper, metaphorically speaking.
Okay.
And try and calculate in your theory what happens to exponential.
We will discuss. We will discuss in your room. Already, I am very suspicious of functional figures, Euclidean functional figures, because Euclidean functional figures don't know how to treat fermions properly. They don't know how to do. They can't treat theta vector. They can't, so far as I know, they cannot treat FF dual in the QCD functional figures. So there are so many things that cannot be treated. They don't know. Then they do some fudging, put model.
Yeah, but
how?
We could simplify things quite a lot by saying, look, no fermions, right? Because we'll understand this simpler problem first, and we'll add in fermions later. And we still can ask that question.
Fermions are, if you throw away half the world,
I'm not worried about that.
But
I'm just.
gluons, okay, let me take gluons.
Yes, okay.
I should not be an opposite, attack them, let them do what they like. But I do know that for gluons there is no confinement mechanism, not even suggested.
But what Genjo said then applies. If you have no fermions and you have just got gluons, right? Gluons were meant to be zero mass particles. If there's a mass gap and there are no zero mass particles, then you could say the gluons are not there, or if you'd like to use the word, confined. You come to Genjo. So
if you want to say, I don't know why there is confinement, okay. It's okay. There are many voices in the world, so it's okay. What did, who says, let 1,000 winds blow? Don't ask me to accept all this, but let it blow. That's what Mao said.
yeah.
So I don't mind. I don't think it is very coherent, but let it go. Why not? Okay. So I want to. So basically, I will finish this with this. So I want to consider a very simple case where I want to diagonalize in the complete community set lambda 3 and lambda 8. So in the three representation, because it is very simple, these are 3 by 3 matrices, and the joint eigenvalues are for the two operators 1 1 minus 1 1 and 0 minus 2. Okay, the lambda 8 is the hypercharge operator. Its eigenvalues are 1 1 minus 2. Okay, so the joint eigenvalues are like this. Okay? 0 0 minus 2, and these are the three vectors, labeling vectors of the complete community set in my superselection set. Okay, and I want to see how they evolve if I put an appropriate term in the Hamiltonian. Okay, with that I will stop because it's almost enough. So I want to put an operator which is this operator, mu1 lambda 1 plus mu8 times lambda 8 is a root 3. Root 3 is because of the standard normalizations. Is root 3 lambda 8 which has eigenvalues 1 1 minus 2. Okay. Lambda 8 has a trace, lambda 8 squared is 2. So for normalization purposes there is a root 3. Yeah. And I want to choose mu1 over mu8 to be irrational. This is a generic choice. The two things, it is important to put lambda 8, I checked this morning, because with this choice, if I exponentiate this h1 in time, by the way, h0 and h1 commute, so I can and there's no problem in exponentiating. You can exponentiate zero, exponentiate h1 separately. They commute. So, and because I have chosen mu1 and mu8 to be irrationally related, the exponential of this operator in t never closes. Okay? It goes on and on and on, circling. In fact, it is worse. I am choosing lambda 1 and lambda 8 from a particular Cartan subalgebra, namely the one which contains lambda 1 and lambda 8. There's a particular, they span a two-dimensional Cartan subalgebra of SU3. I exponentiated. It happens that this orbit I am writing by exponential ITH1 goes on and on in SU3. Okay? This is the SU3 element. Never even comes back to the original Cartan subalgebra. It accumulates somewhere else. Okay? Since the whole thing is compact, it should be accumulating somewhere so that the closure is something. What is that? Generically, I don't know. Okay? However, we considered briefly, I think last week, Thursday or something like that, Brian and I were discussing this. So this is all the time evolving operator in the SU3 language. And of course, this in the quantum state where I have eigenvalues 0, 0, 1, so only the lambda 8 survives, this will do nothing because lambda 1 commutes with lambda 3. The lambda 1 will be 0 here. So this is in that particular basis where I diagonalize the corresponding Q cascade in the superselection sector, this operator will not do anything. But in the other two, what it does, for example, if I put lambda 3, for example, there, and then diagonalize it, the evolution here, lambda 8 commutes with it. What lambda 3 does, this orbit creates the orbit. You remember this is all in SU2, and I am picking one particular element, lambda 3 of SU2. So the orbit will be into 2 sphere because it is SU2 or U1 is a 2 sphere. So this orbit is circling in SU2. The preliminary calculations which we did on the blackboard seem to suggest that the orbit, for example, if we call the lambda 3 diagonalized state as a north pole, it starts circling on this particular 2 sphere, and it circles and circles and circles and circles, and it seems to be accumulating at the south pole. If it accumulates at the south pole, it's very interesting because that will be the fixed point, not at least asymptotically a fixed point of this evolution. That will be very interesting because at other point, if that is the case, the closure of this orbit, the orbit will near the south pole, there will be any infinitesimal neighborhood of the south pole will contain orbits of this kind. So you say that the system looks like accumulating at the south pole. Okay? So if it is really accumulating at the south pole, there's again a state which does not evolve under this chemical potential, and that will be a deconfined phase, okay, in my language. So maybe the deconfined transitions are fixed points of this evolution. But there is something I did not tell you. Why are we calling this color confinement case? Yeah. This is happening by my choice of mu1 over mu8 being irrational. That's what happens also in the torus case, where you choose your orbit at an irrational angle to the square representing the torus. Okay? So if you choose it like this, it goes on winding and winding, and you get a real line embedded in the torus. Okay? So why am I calling it color confinement? If you take any colored operator, the experimentalists do not make instantaneous measurements, period. I talk to people doing experiments in LSC. Okay? They only get averages over the interaction time of any observable they look. So if you take a colored observable and take this case, it's an ergodic or the colored case, you will only get the average of this observable over the interaction time. What is interaction time? 10 to the power of minus 23 seconds for strong interactions. So you are getting something out which is the average of this interaction time. But the average of this over the interaction time is 0 for a colored observable, very much like in the ergodic hypothesis is stagnant. The average over the ergodic evolution of the Hamiltonian is the same as the phase space average. This exact analog of that, and it's trivial to do some calculations, and you get 0. So this looks to me as a substitute in this language of what is meant by color confinement. Now, if it happens that you choose the mu1 over mu8 to be rational, situation changes. I say, because then the orbit I am writing, with which the diagonal state is evolving, has a finite period. After a certain time, it will return to the original torus. So, in that case, the average will not be 0, and we can calculate. I have not done the calculation, but there are also cases where it doesn't change at all. As I told you before, there nothing happens. So, clearly, this model shows that, assuming this model has physical relevance, shows that QCD has many phases, like QED has. By the way, the fact that QED has uncountably many phases is already discussed in Hart's book. If you have not seen Hart's book, you are losing something very beautiful. It's an extraordinary book where, in passing, he also discusses this issue and it discusses how what is the importance of cluster decomposition. What is how in the vacuum you can see that there is electric charge by putting the positron behind the moon. So all these things are discussed there. But he also mentions the fact that QED has an infinite number of phases, and QCD we are again coming to that. And this calculation I am show you, if it is correct, that QED also has an infinite number of QCD also has an infinite number of phases, and they are qualitatively different. In some, the color observables will give 0, and in the others, it will give nothing. I mean, it will give some average value, you can calculate, and you can actually find some average value over the interaction time of the observable you are looking at. So there are both these possibilities. There is a color confinement phase and color deconfinement phase. Now, I don't know. So I think I have exceeded my 1 hour, but I don't know experimentally what is the situation. What I have heard is the following. I have heard that the quad-gluon plasma, by discussion, they do have color confined and color deconfined phases. But whether that has anything to do with actual color, I don't know. Denjo says no. I don't know. But I do know also that when people do quad-gluon jets calculations, in each jet there is a color, no doubt. So all the and they are done in perturbative QCD with a very elaborate calculations of handling divergences in renormalization, very elaborate heroic calculations of quad jets. But at the end, each jet has a color. Then they bring in some smearing functions from outside. It has nothing to do with QCD by hand. There's a whole industry which combines this color into a singlet. That's put in by hand. Because of I suppose, if they don't put it in by hand, what will happen? I don't know. This I don't know. But that's what they do. So, do we use quarks in phenomenology calculations? Actual existence of quarks? The answer seems to me yes. Nobody says that infrared effects are unimportant. They put in quarks, but at the end they smear it out with some outside data. So I don't know how to think of these things in a coherent way. But anyway, this is my understanding of, my evolving understanding of the work we have been doing for a while. So I think that since I have exceeded 1 hour, yeah, I have.
That's okay.
I'll stop here and I'll ask that because I'll now jump into another topic. Okay. So I'll stop here. I have had something to say about the importance of these test functions for experimental observations, but I think time is.
Yeah, it may be appropriate. So if this is a good place to break, then let's break.
It's a good break, so I'll stop here.
Then let's draw let's thank Val for small. Appropriately provocative and stimulating. So, and the other.
Yes, I would rather be right than provocative. But I want to say, because anomalies, it's not the axial anomaly. Okay? There are infinitely many anomalies, okay? Of which the axial charge changes the domain of the operator, or the operator which is given by the vector charge. That's all. Okay?
Yes.
But there are a huge number of other operators which do the same. They are all anomalies. So I can ask her questions in that context. I don't know the answer. There are uncountably infinitely many anomalous objects.
This is a question to Saki.
I am telling her, that's a fact. You will see it already in Hubb's book. It's not a great thing. Anomalies are not. How do they produce zero modes? That is more mysterious. I checked in some particular cases that the index theory that comes from the axial anomaly, space-time Dirac operator, coincides with what I get by this kind of calculation. I don't know why. This calculation is very simple. Look at the Dirac operators, look at the zero modes, they are there. Are they stable under this superselection operators? They are stable, they don't go away, they are there. So there is some theory there which I don't know. Maybe these people, Moon, Rare and Shaw, knew it. They are much more powerful mathematical physicists than I am. I don't know. But regarding anomalies, no problem. They are all over the place. And who said it? Vaughan Jones said that I don't know about algebras, but wherever I see Polynomial algebras. That's what he said. Here, I don't know about anomalies, but wherever I see objects which change domains. So, already particles are accepted. You don't need it. There are a lot of operators which change particles on the domain of the operators, but particles are uncertain. They are all anomalies. Okay? So, in the general framework. So, there's a whole lot of insights which come from these discussions, which I think definitely are worth thinking about.
Okay. Questions?
I'll make one more question since I've made too many already. So if I simplify things that you consider QED, right, rather than QCD, then you say that there are all these spaces for QED, right?
I'll get on this better than a hear you problem. Unfortunately, my hearing is short.
Okay. So if we talk about QED, to make things simpler, instead of QCD, you say that there's all these spaces for QED. Right? And so my humble question is, what's the experimental situation? How can you look up an experimental book and see when they measure these?
I think this is a question which we have been battling with for a while in QED, because one knew already from Tom Kibblesberg and even before that they are coming from infrared clouds in their shapes. How infrared clouds, there are infinitely many infrared clouds. They change small frequencies.
Are there any experiments?
So how do I see experimentally? What does it influence experimentally? The answer I would say is, I don't know the generic answer, but I have looked at theta vector, which comes from U1 symmetry. And there I have found out that there are particular effects which you can see. So your answer is well taken. I don't know. I would like very much. There's a scale in the problem. Namely, in the Hamiltonian, I'm adding the energy scale. So I suppose that somebody who is really clever will say that the way I coupled the experimental apparatus to the system sufficiently strong will show these effects. I suppose. Or if there's a proper measurement theory, that will show the influence of the scale. It's a scale question. Where is the scale coming from? So I would say that's really an open problem. By the way, this also gives edge things. I can do the same, all these things on a manifold with the boundary. Spatial manifold with the boundary. Because put a gaussian inside, there are a lot of these things. Then these things will happen at the boundary and they will evolve by this game interpretation. Nothing, I don't have to talk about spin orbit coupling, no, nothing, you do it. And there it should be experimentally accessible. Because it is finite system, it should be. So that may be a place to look, but I have not looked at it.
Other questions?
Maybe related to QED. So it is known that in 2 plus 1 dimension, QED is a confining theory. Can you test this by using your approach?
It's not my approach.
Or your way to.
Again, when they say confining theory, they are talking classically.
Right.
I don't want, so you have to look at the Hamiltonian and show that the spectrum does not contain any color state. The only paper or paper might have discussed is this Moon, Raren and Shore. That is an elaborate paper, and they have done some calculations along these lines, looking at the superselection sectors and how they intertwine and so on. So they may have an answer. I have not looked at it.
Other questions? I have to disagree with it that those are classical. I mean, if you put in two operators and an operator that represents a quark and an anti-quark, and
You can't bring them. You can't bring them.
I don't. Why not? Why do they are external operators? They're just
They're operators. There is no local operator.
in the algebra. They are operators in the algebra.
But there is no.
They are.
You can steer it at some point.
I speak of them, yes.
But whether they are localized or not depends on the stage. It's simply an operator. So.
But the question is, how does the energy grow as I separate?
Let me tell you, disengage you from this problem immediately. There are no localized states whatsoever in quantum field theory.
I didn't say that.
So you say quark is here, there is no such
I
thing.
didn't say that. Its center is here, and there's
no such thing.
No.
That means a quantum expectation value gives you that center. Yes, there is a quantum state which is localized there, and another quantum state is localized there. In quantum mechanics, there are such non-relativistic quantum mechanics, there are such states. Here, there is none. That is one of the deep results which actually came from old papers of relativistic point particle interactions by actually George Sudarshan and Tom Jordan and Mukunda and so forth. And it developed into a whole series of papers coming from an experiment of Fermi.
I don't think we're communicating correctly.
There are no, let me say, there are no projection operators.
I didn't say it was a projection operator.
There is no quantum state which will test for you whether such an operator is localized somewhere because of the Reed-Schreiber theorem.
But I don't need it to be localized.
But you say there is a quark field there. Quark field is not
In this
observable.
region.
Huh?
In this region.
You can't see it. It is simply an operator.
It's an
Simply an operator. What do you do with it?
It's smeared operator in this domain.
Again, let me remind you, if I apply these operators on the vacuum, I generate a dense set of vectors in the Hilbert space.
You do, yes.
Yeah. So, is it localized there? What do you mean? Just act with that, all such operators in your chosen space-time region on the vacuum, then I can test what is happening for expectation values here. And I guess it will be reflected in the expectation values here, far away.
They will be correlated. They will be correlated.
No, is that the space-time things. Okay? So I take your thing, you do all this, and look at a space-like region separated from that, and measure observables there. It will tell me what you have done. Because
That's a separate thing.
so there is no sense in which I can say a quark field is there. That statement by itself has to be qualified as an operator. I can't see it.
Well, that's too strong.
Yeah.
That's far too strong a conclusion. That doesn't follow from what you're saying, even if I believe all the stuff.
How do I know an operator is here? I had to apply an operator state on it. Yes. And the state has to tell me that the operator is here, not somewhere else.
Yeah, but then you can still ask this question, and you haven't really answered it. Then you can still ask this question.
You can ask, but there's no answer because of the Reed-Schreiber property. You can ask anything, but the Reed-Schreiber property says you can't do this. In fact, that led to this famous Fermi experiment, which was causality violating. You know what Fermi experiment is? I think I talked about it here. It's a Chicago lectures. He took two atoms which are separated. Okay? One of them is in excited state, the other is in the ground state. Okay? And they are separated by some distance L at time 0. He said that leave them, and the second atom cannot get excited before time L over C, because of the fact that time of propagation is L over C. So causality remains that the second atom cannot get excited for time before L over C. He said that. Quickly it was found out that to do this, the second atom can never get excited. Never. This is the famous Fermi experiment, which was solved much. So the whole assumption comes by thinking that the Hilbert space is factorizable like that, which is not possible. So there are no projection operators like this in quantum field theory. It is coming from the fact that the Hamiltonian is bounded below. There are corresponding results in quantum mechanics because of the fact that quantum Hamiltonian is bounded below. We cannot localize in quantum mechanics H bounded below this. You cannot find a state is localized in a time interval. There is a corresponding statement, and it comes from analyticity arguments. This is the weak shader theorem. It is not correct to think about quantum field theory as we do classically. Somebody sitting here to sit in the. It is not possible. It is not like that. It's much more to infer those things. There's a long series of things. And I don't think that even classically they have a measurement theory. I don't think. There are problems there. The Kolmogorov. So, general feeling is that the classical theory is controlled by commutative algebras and some states, Kolmogorov axioms on probability measures. But there also we are looking at commutative algebras, say phase space. We look at functions on the phase space. We don't measure x and p on phase space. We measure a function on the phase space, and you have a probability measure, you take exponential values. But there are many such, and they are commutative because it's point-wise multiplication. How do I know there is a phase space? So which algebra do I take? There are a huge number of them. The hint in the direction we are talking about came from this Gelfand-Neumann theorem. The duality, it says that if you have a commutative system algebra, the spectrum of that algebra, the space of irreducibles, gives you a Hausdorff topological space. Okay? So, it is not exactly our topological space, but it has the property that you can separate points by openings. Then came all this tremendous papers of Alain Kuhn, where he reduced the Dirac operator. Then Tomita Takesaki theory. Then eventually he was able to prove that you can recover the entire differential geometry from the commutative algebra. That is the Matilde Marconi code. But when I look and I see that I am not using Dirac operators and Tomita Takesaki theory to infer, I am doing something else. What am I doing? I don't know.
I don't know either.
Yes, actually, our formulation is completely wrong. Okay? The phase space f of xp, right? Cos of x. Apparently, that is not what we are looking at. I don't know what. What is the brain? How is it connected to that? I don't know. I think this is. So, what I have done here, I have tried to do, is to recover a commutative algebra from the superselection sectors, which I think I have. Does it give a measurement theory of quantum mechanics? No. Well, maybe. But this problem of how I see nature at all, I have no idea. Maybe we should go to Kant, but she was objecting Kant. Because these are the problems of people like Kant.
You mean the philosopher?
Yes.
He's dead now.
He was talking about irreducible minimums, and he was
I could bring him up if he was alive. He's not.
he may not know physics, but he thought deeply.
Well, I think the discussion has degenerated a little bit, so I'm going to stop the recording.
Okay.
We can continue, but I'm going to.
No. I'm done.
I'm sure Kant is still alive as well.